Hey, it is 11:30. I just hit record. Let me confirm that the mic is working. Mic is working and I'm unmuted. Okay. Last Thursday, we of course started a new topic, thermochemistry, which we had described as being a topic about the energy of a reaction. We went over a few key details about thermochemistry and its information, which is primarily centered around the idea that energy is either released or absorbed. Most reactions either release or absorb negligible amounts of energy. What that means is more often than not, it will be not noticeable, at least to the naked eye or to human sensations, that if energy is being released or absorbed. But there are a few cases where the reaction is a little bit more obvious. For example, a hot or an ice pack or a bomb. Within that vocabulary, we can describe a reaction as either exothermic or endothermic. An exothermic reaction is defined by the fact that energy exits, in other words, overall released. As a result, it results in an increase of temperature and has a negative energy value associated with it. Endothermic, from the word endo or phrase up from the part endo, energy enters. The energy is overall absorbed, temperature decreases, and has a positive energy value associated with the reaction. Now, as of Friday's workshop, you've had some hands-on experience with the different types of calculations that will appear in this chapter, but I just want to remind you a key detail about the negative and the positive symbol. The negative symbol, yes, it is a reflection of the math behind the calculations, of course, but it's also a reflection of the direction of energy. For example, in an exothermic reaction, a negative energy symbol is used to imply that energy exits, that it leaves. In contrast, the positive is where it enters in the opposite direction. So in thermodynamics, we talk a little bit about the direction of a reaction. We went over standard enthalpy of formation, energy profile diagrams, the technique that we will perform in lab for thermochemistry, and of course, Hess's law. Today, we're switching up gears a bit. We're starting a brand new topic. We'll be spending the entirety of this week on it. This is what's known as chemical kinetics. Maybe some of us are already able to tell what this is all about based on the word kinetics. But just as how thermochemistry was a study of the energy of a reaction, chemical kinetics is a study of the speed of a reaction. Here, of course, I've abbreviated reaction to RxN. Now, one of the basic guiding principles behind chemical kinetics, or rather understanding the speed of a reaction, is understanding what is known as collision theory. Collision theory, plainly put, is a theory or model that explains the rate of a reaction on a molecular level. Collision theory, as the word suggests, it talks about the actual collision between the molecules. It is from this collision how bonds are broken or formed. It's also from these collisions that energy is either released or absorbed from. Collision theory has a few requirements that need to be met. In other words, for a successful reaction to take place, the following conditions must be met. Number one, to no one's surprise, the molecules must collide. They have to make physical contact with one another, and the way they do this is through literal collisions, just as how a car would crash with one another. molecules must collide. Number two, the molecules must have sufficient energy. So not only must these molecules collide, they must be heading at each other at sufficiently fast speeds. Why? Because they must overcome that activation energy. Remember from last week's topic of energy profile diagrams. The activation energy is the hill that the reactants have to overcome. So the molecules must have sufficient energy to overcome the activation. Finally, the molecules must be in the correct orientation. Now, the first two requirements should make sense to us intuitively. Of course, for anything to form or break, there must be some sort of collision. And of course, they must be traveling at some speed or energy. Otherwise, they'd just be quite literally frozen in time or place. But this is the first we've seen of such a thing called correct orientation, at least for the requirements of a reaction. So what does that exactly look like? Well, if we take, for example, a popular reaction, the reaction between carbon monoxide and oxygen to form carbon dioxide and oxygen, just a plain oxygen, we can understand a little bit more about this idea of orientation. If I were to draw a pretty basic graphic representing our carbon monoxide and our oxygen, like so, what we would see is based on the orientation of these molecules, the collision would take place between two oxygen atoms. This actually leads to no reaction overall. But if we were to slightly flip it, oxygen, 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 carbon. All of a sudden, these molecules are correctly, or at least appropriately oriented, such that they're able to achieve a head-on collision, such that we do form our CO2 and just a plain oxygen atom left over. Sorry, I mixed up the colors. So my hope is that this very simplified graphic shows us the importance of why these molecules need to be correctly oriented to one another. Because otherwise, the collision, well, it just wouldn't be productive. So what does this collision depend on? Remember, so far what we've talked about is that collision theory is a model that explains the rate of a reaction, at least on a molecular level, and there are a few requirements. But what does the actual collision depend on? Well, number one, temperature. At higher temperatures, molecules are able to achieve a higher speed. In other words, the hotter the reaction, the faster the molecules. We're also looking at concentration. Going back to that car analogy of them actually colliding, if there's a whole bunch of cars on the highway all going 100 plus miles an hour, there's bound to be a crash or a collision sooner or later. And finally, molecular size. Again, following the analogy of the car, a crash between two semis would, of course, be a lot more disastrous than between two bikes. The collision still occurs, of course, but the force of the collision and the resulting energy depends on the size of the molecules. So that's collision theory. For its reaction to be achieved, for a reaction to occur, the molecules must collide. They must collide with a certain amount of energy, and they must be correctly oriented. How does this better help us understand the concept of reaction rates, our next topic? Well, we can actually give a very simple definition to rates. We can define rate as a change in concentration all over a change in time. In other words, we can write this as delta molarity all over delta T. We, of course, know that the unit for molarity is at just that capital M, aka moles over liters. But the thing about time is that, well, time can have any particular unit. Sometimes it'll be seconds, sometimes it'll be minutes, hours, days. I do know some reactions that have like a yearly check-in progress, check-in point. But this is a standard definition of rate. It is the change in concentration over the change in time. Now we're going to draw a graph. On the x-axis is time. And for the purposes of this example, we're going to set the time units to seconds. And our y-axis is molarity, which of course has units of moles over liters. Now, of course, the x-axis is the time, of course, the very beginning of the reaction to when it ends. At the absolute beginning of the reaction, at that basically time equals 0, we should have basically nothing but reactants at the very, very start of the reaction. Similarly speaking, at the very, very start of the reaction, we shouldn't have any product. I've just kind of drawn it a little bit above the line for the purposes of this visualization. But hopefully we understand what I'm trying to say. At the very beginning of the reaction, we should basically have 100% reactants and 0% products. Our hope is by the end of the reaction, we have 0% reactants, basically that everything has been converted. On the other hand, we hope that at the end of the reaction, we have nothing but products, such that that is now in 100%. This is an ideal case. As you all have seen in labs, sometimes the reactions don't work out the way we expect them to. The yield is sometimes a little bit above or under 100, but this is an idealized case. We're, of course, able to connect these points that actually tell us a story, or rather a direction. In fact, what this tells us is that over the course of the reaction, the reactants decrease. And over the course of a reaction, the products increase. Let's take a very sample question. The question simply reads, in a reaction, just abbreviated to RXN, the concentration of H2O2, hydrogen peroxide, decreased from 1 molarity to 0.5 molarity over 6 hours. Calculate the rate of decomposition. Okay. Taking it all together, looking at the graph, looking at our formula for rate, we can go ahead and plug this in. We can simply say that rate is equal to the change in concentration, specifically talking about H2O2, all over the change in time. We, of course, know that the definition of change is final minus initial. Here, just labeled as F and I, final and initial, such that we're able to say this is equal to 0.5 minus 1 all over 6 minus 0. Where do these numbers come from? Well, think about the wording of the question. It told you that the chemical decreased from 1 to 0.5. So clearly the initial amount was that 1 molar. The final amount was 0.5. And it took place over 6 hours. We don't necessarily need to know the starting and end time. The fact that it starts at 9 a.m. and ends at 3 p.m. is kind of irrelevant. The change is 6 hours. You're told as much. If we go ahead and put this into our calculator, 0.5 minus 1 all over 6, we actually get a negative number. Specifically, we get negative 0.083, where the units are, of course, molarity over hour. How do we know it was hour? Because the question told us that we were working on a scale of hours. Remember, time can be seconds, minutes, or hours. It just depends on the question or the context. Now here we have a negative symbol. And the negative symbol, of course, is a reflection of the math. 0.5 minus 1, smaller minus larger, is in fact going to be negative. But does the negative make sense? Yeah. I mean, think about it. We said that the chemical decreased. The very wording of this is what suggests that it's a reactant that's decreasing. What do we have here? We have a negative slope. The fact that it's negative is not only a reflection of the math, but a reflection of the direction as well. Just as we saw in thermodynamics. The negative symbol is not a red flag by any means. It simply tells us this is a reactant that's going down. And the negative now makes sense. Of course, we use up the reactant, so we expect it to decrease. We, of course, expect for the products to have a positive slope and a positive rate as well. So this is now the second topic that we've seen, that the negative and positive sign not only reflect the math of it all, but also something about direction. Let's talk about factors affecting reaction rates. These factors are given in no particular order of importance, starting with concentration. A higher concentration, higher molarity, higher whatever you want to call it, leads to more collisions per second. Remember that collisions are really what preempts a reaction. There needs to be a collision in the first place for there to be any sort of reaction at all. So a higher amount of your chemical leads to more frequent collisions. Number 2, surface area. The idea behind surface area is that an increased surface area, or more surface area, means more collision sites. More opportunities and locations to collide. The concept behind surface area actually explains why we crush medications. Because they're in theory supposed to lead to faster relief. You've probably crushed some tablet to kind of put in your water. Maybe some of us take like sleep aids, crush it in our night tea, whatever. Help us fix a hangover. That fine powdery substance allows for more collisions than just a straight solid tablet. Number 3, temperature. This one, of course, we've slightly discussed over today's lecture, but just so we give it some formal description. Higher temperatures lead to faster molecules. Faster molecules means more collisions. In fact, it's been well established historically that a 10-degree increase is known to double the rate of a reaction. This basic idea is why we refrigerate food to slow down the spoiling process. It's why if the recipe says bake at 350 for an hour, you can just bake at 375 for 45 minutes. Higher temperature leads to more frequent collisions and more reaction overall. Number 4 is called catalysis. A catalyst, as it's called, is a substance that increases the rate of a reaction without being consumed itself. What do I mean by it isn't being consumed? It means it is used and recycled. How exactly does a catalyst work? We're actually going to draw a graph. Let me copy this over to another page. On this graph, on the y-axis, this will be energy, which we know from last week is traditionally in kilojoules over mole. The x-axis is in time, which of course could be seconds, minutes, hours, or whatever. For a generic reaction, let's just say, doesn't matter if it's endo or exothermic, we can place the reactants and products appropriately. And we can, of course, draw a curve connecting them that captures all of our basic facets, activation energy, enthalpy, blah, blah, blah. What I'm actually going to do is I'm going to lower this P a little more. I want to make it a little more pronounced. 1 second. P right here. Yeah, great. In black is our uncatalyzed reaction, meaning no catalyst present. This is our normal reaction pathway. This is our normal hike. We have to overcome some activation energy so that we can get to the products. As we've talked about, if you don't have enough energy to overcome this, then there's no reactions going to occur. But the way catalysts work is that they provide you with another pathway. Notice it takes the same shape, that nice curve with a clear height, but in a catalyzed reaction, an alternate pathway is provided. One that's considerably shorter overall, or more specifically, one that's easier to overcome. If you've ever taken a biology class, you've probably seen it in that class within the context of enzymes. Enzymes are a classic catalyst, a biological catalyst. And if you've ever taken this class in biology, you know, of course, that enzymes work by either a lock and key fit or an induced fit. If these terms mean nothing to you, don't worry about it. These are explicitly biology. I'm not going to ask you details on how enzymes specifically work. But it is good for you to know that enzymes in general are a good example of catalysts. Do we have any questions so far? Okay. Let's put some numbers to this. Let's talk about rate laws and expressions. For a generic reaction, here written as A plus B gives us D plus E. Super generic reaction here, just using letters to get my point across. Where the capital letters are, of course, the chemicals, and the lowercase letters reflect their balancing, meaning 1A, 2B, or 3. Sometimes it could just be 1. The generic rate law, or rate expression, of this reaction is equal to K multiplied by the reactants where each reactant is raised to the power of some number x and y. We, of course, should know that those square brackets refer to concentration, aka molarity. And this new term K is a rate constant that depends on the reaction. We've seen a lot of constants so far in this class. Most notably, we've seen the specific heat capacity of water. We've also seen the gas law, the universal gas constant. In those cases, specific heat and gas constant, those were specific numbers that never changed. For the rate constant, it simply depends on the reaction at hand. The two new things established here is this X and Y business. X and Y are defined as the order of the reaction with respect to, here I've abbreviated to WRT, with respect to each reactant. Based on how it's written in the rate law, X is the order of the reaction with respect to A. Y is the order of the reaction with respect to B. This X and Y values is not equal to the stoichiometry values. If they happen to match, that's just a coincidence. But they are not explicitly the stoichiometric values. In fact, they can only be determined using real data. And by real data, we of course mean I need to give you some information about the experiment, and only then can you identify the rate constant as well as the orders. The only other thing you need to know about X and Y is that the sum of the orders is the overall order of the reaction. Now, what these values, X and Y, physically represent is that they reflect the sensitivity of the reaction. Sensitivity of a reaction by a chemical. See, while it may be satisfying to think, well, both reactants affect the reaction equally, 50-50, the truth is very much not so. I mean, think back to reaction metrics when we talked about limiting reactants. Both reactants do not affect the reaction equally. So more often than not, maybe one chemical is more sensitive than the other. What does that mean? What does that look like? How do we determine rate loss? We're going to do a sample question. The question is based on the following reaction. This is the reaction between NO and ozone, O3. That's not O2, that's O3. And that leads to NO2 gas added to O2 gas. The question simply states, provide the complete rate law for the reaction based on the data below. I'm going to draw a table. This table is going to be 4 columns, 4 rows. The headings for the columns are as follows. In the first column, we have trial. In the second column, we have the concentration of NO. Third, the concentration of O3. And in the fourth, we have the rate. What immediate things I want you to notice is that the rate is defined to you as molarity per second. The S is second. So we already immediately know what time unit we're working with. I'm going to give you data for 3 different trials. Trial 1 has the following numbers. Trial 2, the following numbers. And finally, trial 3. Yep, I think we're good on space. There is a complete question. I'll give you guys just a minute or two just to be sure you copied it down in total. Okay. I'll still keep the table in view so you can write in the numbers if you haven't yet. Ultimately, what the question is asking us for is to provide a complete rate law expression that follows the format rate is equal to the rate constant multiplied by the reactance raised to some power x and y. This is what our final answer is going to look like. We need to write it in this form, but to do so, we need to find x, y, and k. So whenever the question says, provide a rate law expression, it's really asking you, you need to find these 3 things, determine them, and then write it all in one full, nice statement. Here we have an example of a question of what I was talking about. Since rate and its rate constant depends on the reaction, can only be determined using real data, I do have to provide you with data. Now, you're at the point in the semester where on a fundamental level, you should understand the reaction, reactants, products, state symbols, balancing. We're at the point of the semester where we're analyzing reactions now. Last week we did thermochemistry. Now we're looking at kinetics. So how exactly do we do it here? Now, to determine the orders, there unfortunately isn't an explicit formula. In fact, it's a little bit more of a logical approach. The idea is if we want to find out how much NO affects the reaction, we need to look at two trials where NO changes, but the oxygen does not. What exactly does that mean? What is that? Why do we do that? Well, I'm going to go ahead and give us a spoiler alert. The two trials that we'll be picking is trial 2 and trial 3. Here's why. As we can see in the data for trials 2 and 3, there is no difference in the ozone. There is, of course, a difference in the NO. The reason why we pick these two trials is because we can say beyond a doubt, any change in this chemical is what affects the change in rate. Why? Because the other chemical is a constant. Again, by changing the concentration of one chemical, only one, we're able to say any change in rate has to be because of that chemical. So we are going to pick two appropriate trials We're starting off on the left with NO. So I'm just going to put this nicely in a box so we don't forget it. And the trials we picked, I will simply write T2 and T3, where of course T stands for trial. We are going to compare the two, trial 3 over trial 2. And we're going to say, based on the given information, the concentration in trial 3 was 2 times 10 to the negative 6. Where does that come from? Straight from the table. It's in trial 3. In trial 2, the concentration is 1 times 10 to the negative 6. Why did I put trial 3 on top? Why not the bottom? Simply put, you tend to put the larger concentration on top. By putting the larger concentration on top, you avoid fractions. So those are the concentrations. We can see how that affects the rates. In trial 3, the rate is 1.32 times 10 to the negative 4. And the rate in trial 2 is also 1.32 times 10 to the negative 4. Notice I'm using that ratio to make it clear. We're looking at what the change is. When we put this in our calculators, over here on the left, maybe some of us are able to do this in our head. 10 to the 6, they cancel each other out. This is basically 2 divided by 1. This is just 2. When we compare it to the rates, well, the same number divided by itself is just 1. We are now going to reduce this ratio to 2 to the n, 2 to some power. 2 is equal to 2 to the 1. And 1 is equal to 2 to the 0. Remember, anything raised to 0 is 1. And here's what this mathematically tells us. When we double the concentration, nothing happens to the rate. So does this chemical affect the rate? No. From the powers, we're able to see this is 0th order. There is not an explicit formula for this type of question. You pick 2 trials and you analyze it. You see, some of us may have already been able to look at the table and say, well, Supreet, did I really need to go through all of this work? Couldn't I just have looked at it and said, well, this multiplies by 2 and no change happens to the rates? Doesn't that immediately tell me this is 0th order? Yeah. That's why there is no explicit formula to this. It is an analysis of real data. This is the written analysis. You compare the trials, you compare the rates, you reduce to the power of 2. But sometimes you can just look at the table. This is the order of the reaction with respect to NO. All we have done so far is calculate X. We are now going to do the same thing, but for O3. I'm going to bring the table back. Let me just move it over. That way I don't need to keep swapping back and forth. All right. Remember what we're going to do. The first thing is we are going to pick 2 trials. We're specifically focused on the O3. So we are going to pick 2 trials where the O3 changes, but not the NO. There's only 3 options. Take a scan for yourself. Don't shout out the answer. Just take a scan for yourself. We're looking for 2 trials where O3 changes, but not NO. Hopefully we all come to the same conclusion. We're going to be looking specifically at trial 1 and trial 2. We can see that O3 does change. NO does not change. Remember why we do this is because we're able to say that any change in O3 leads to a change in rate. That's how we calculate the order of the reaction with respect to O3. Now, visually, you're able to say, well, yeah, I do definitely see a change. The rate changes as well as the concentration. So there is some order here. There is going to be some number. So let's go ahead and calculate this. We'll actually be using trial 1 and trial 2. We're going to put the bigger number on top. That's what tells us trial 2 on top over trial 1. From the data table, the concentration in trial 2 is 6 times 10 to the negative 6, all over 3 times 10 to the negative 6. The rate is 1.32 times 10 to the negative 4 for trial 2. The rate of trial 1 is 6.6 times 10 to the negative 5. Where does this data come from? It comes from the table. We're going to simplify this now. Over here on the left, the 10 to the 6s cancel each other out. So 6 divided by 3, that's just 2. Over here on the left, we have a slightly more complicated looking numbers. We have decimals and scientific notation. So let's calculate it to be sure. 1.32 times 10 raised to the negative 4 divided by 6.6 times 10 raised to the negative 5. That's a flat 2. We are then going to reduce these numbers to some 2 to the n. This is 2 to the 1, gives us 2 to the 1. What's another way we can say this? When the chemical doubles, rate doubles. Based on the order, the powers, this is 1 to 1. This is what tells us this is a first order. What do these orders mean? Remember, they reflect the sensitivity. First order tells us that when the chemical doubles, the rate doubles. It's a 1-to-1 ratio. If the rate triples, the concentration triples. Over here, we had 0th order. 0th order tells us, well, it doesn't affect the rate at all. We can double, triple, quadruple. The rate will stay the same. 0th order. With that, what we actually have so far is rate is equal to some constant K multiplied by the reactants, each raised to some power. 0 and 1. All of what we just spent time on analyzing it was to calculate the orders. Now, just as before, I have the table right here, actually. The reason there is no explicit formula is because you are, in theory, able to analyze the table without it. For example, our more math-inclined students would be able to quickly recognize, well, concentration doubles, rate doubles. That's just 1-to-1. That's first order. What if, so just what if this doubled and the rate quadrupled? What would the order be? Second order. This is a 1-to-2 ratio. If this was doubles, and I believe this is hextuples, this is third order. So don't let these exponents really freak you out. I give you the written process so you're able to get to nice, simple numbers. But as you get more and more practice, and trust me, you will, based on this Friday's workshop, you'll be able to do this kind of stuff just with your calculator in hand. I see a hand. What's up?
When you reduce to the number to the end.
So generally that just depends on the identity here. So for example, if I had given you such a, this is 3 to the 9, then you would try to reduce this to 3 and 3. So it just depends on the specific numbers we're dealing with. More often than not, it'll be powers of 2. But yeah. Are we done? No. Why? We still have to find K. See, here's what we know based on the equation. We know that rate is equal to that whole bunch. So what we can do to find K is actually we can just divide both sides by the reactance. That cancels out, such that we're able to say K is equal to rate divided by the concentration of NO multiplied by the concentration of O3 raised to some power. Okay, so now we have an explicit formula for K. All I really need now is to know what the rate is and what the concentrations are. Wherever will I get that data? Oh, would you look at that? Here in the table, I have 3 different trials that tells us the rate as well as the concentrations. How do we know which trial to use? Does it matter? No. Why? Because what did we establish? We established K just depends on the reaction. So in theory, whichever trial we pick will lead to the exact same K. So tell you what, let's arbitrarily use trial 3. I'm just picking trial 3. Why? It doesn't matter which trial because they all should lead you to the same K. We're just going to pick trial 3. You should have the tables in front of you. I'm not going to swipe back up. The rate in trial 3 is 1.32 times 10 to the negative 4 all over the rate of NO 2 times 10 to the negative 6 raised to 0 multiplied by O3 6 times 10 to the negative 6. What is anything raised to the 0? 1. I'll tell you what, we don't even need to spend time on the NO. Anything raised to the 0 is just 1. That makes sense. Didn't we just determine on the previous page that NO will not affect the rates? Yeah. So the fact that it basically just gets ignored, that makes sense. Anything to the 1 is itself, so we can just leave that as is. Now we're going to do our calculation. 1.32 times 10 raised to the negative 4 divided by 6 times 10 raised to the negative 6. Anything to the 1 is itself, so I don't need to purposefully square it or anything. I see here that this is equal to 22. Now remember what I just told you. I just said that the rate constant is the same regardless of which trial you pick. To quickly prove it to ourselves, we just used trial 3. If we use trial 2, recognize it's the exact same number, so of course it's going to lead to the same thing. Let's prove it using trial 1. It's just going to be the rate divided by O3. Let's put that into our calculator to be absolutely certain. 6.6 times 10 raised to the negative 5 all over 3 times 10 raised to the negative 6. Again, 22. So it doesn't matter which trial you pick, the rate constant will be the same for the reaction. Any questions on this so far? There's more. What about the units? You see, the orders, they're unitless. They're what you're going to power. You're going to square, or you're going to cube, or whatever. Those are just numbers. But the rate constant has units. How do we decide that? Well, from the equation, we had molarity per second. That's from the equation. We had rate on top, and on the bottom, we just had molarity. I'm just using these units just as in the equation. Rate on top, concentration on the bottom. Molarities cancel each other out. We're left with 22 per second. With that, we have calculated all that we need to calculate. All we need to do is our final touches. Our final answer is rate is equal to 22 per second times 03. Where did the NO disappear to? Anything raised to the 0 is 1. So what's the point of including it? Why did I not explicitly write the 1 here? Well, anything left by itself is, of course, implied to be to the 1, so it just wasn't necessary. This is our final answer. Do we have any questions on this? To wrap things up, let's look at our common rate laws. In this class, we will encounter 0th orders, first order, second order, and third order. Although you can go beyond, you can go 4th, 5th, and 6th. That is out of scope for this class. So the extent of these kind of problems will only go up to a cube. That's it for today. We've covered a lot of content of kinetics. When we come back on Thursday, we're going to pick up on kinetics. We're going to talk about integration. We'll be talking a little bit of calculus on Thursday's class. Not too much will be required of you, but come prepared to do some equation manipulation. Thursday, of course, new content will be taught. And then Friday, we have a workshop. If you have any questions, come talk to me now. If not, see you guys on Thursday.